Okay. So today we will talk about heap. And next session we will talk about heap exploitation. We will spend 2 sessions on this topic. Then we move forward to microarchitectural attacks. So you probably remember this figure. This is what the memory map of a Linux process look like in a 32-bit system, especially when there is no ASLR. We have been talking about a lot of those sections in the semester. The text section is where the code is, the data section, BSS section. We spend a lot of time on the stack section. We find ROB gadgets in the C library, which is the memory mapped segment. So far, we haven't really talked about the kernel space and also heap. So in this class, we're not going to talk about the kernel space, but today we're going to talk about heap. So heap is a pool of memory used for dynamic allocations at runtime. If you programmed in C, you probably already use a heap. There are several functions available for you to use the heap. Those functions are C library functions. They are not system calls. For example, you have been using Malloc a lot. Also, whenever you Malloc something, you need to free it later, right? So those two functions, they are C library functions. They are not really system calls. The reason for that is dynamic memory allocation is not the job of the kernel. It's actually part of your process. It's part of the C library. The C library has a dynamic memory allocator. So some of you may have taken CSE 220 systems programming in our department. I believe in that class, you guys developed a simple dynamic memory allocator. So if you are from that class, you know those are not really system calls, but library functions. A little bit about how do we use those two functions. There are several others, but we, for example, there are Malloc as well, but we focus on these two. The first one is Malloc. Malloc takes a size as input and returns a pointer. So this function basically allocates the size of bytes you ask for, and that size will be uninitialized. And you can ask for the size at runtime. So it's not compiler time. It's not like you declare an array of 10 bytes. Then that 10 bytes of array is actually allocated at compiler time. When you compile the program, it will compile into instructions. It is determined. So here, we ask for memory at runtime. So if the allocation succeeds, this function will return the pointer for you to use. The pointer is basically the address for you to use. So when you are done with the memory, the buffer you asked for, you have to free it. So that one, for that part, you use a free function, which takes a pointer as input and doesn't return anything. So it doesn't really give you any feedback if you free that memory successful or not. So the free function basically will deallocate the space, the buffer, previously allocated by the Malloc function. So I have a simple example here to Very simple program. The program has a main function. It has a local variable. The local variable is char star. It's a pointer, and it points to null. So at the beginning, it doesn't point to anything. The local variable itself is on the stack, but its value is 0. Then we do a malloc here. We malloc 100 in hex bytes, and we assign that address to buffer. So buffer will point to whatever you malloc it. Then you can do fgets, whatever. You can put data there. Then you can print it out. Then after, when you are done, you don't need this buffer anymore. You need to free that buffer by doing this. Of course, you will say this program is so small, it's going to return 0. The program is going to exit anyway. Why do you need to do free? That's true for this small piece of program. For this small piece of program, technically you don't have to do free because the program is going to exit anyway. But for large programs, millions of code runs there for days, months, or years, you should always free the buffer you don't want to use anymore. Otherwise, you are going to lose a lot of memory constantly. So what is different between heap and stack? Heap we're already familiar with. If you want to use some buffer on a heap, we have to use fixed memory allocation, and that is done at compiler time. You either define a structure, an array, something like that, whose size is known by the compiler. So the compiler can allocate space at compiler time. So stack are usually for local variables, return addresses, and function arguments. Stack is fast, and also stack is automatic. You don't have to explicitly manage the life cycles of variables on the stack. So when you define for example, here we have a buffer. This buffer, the pointer of the buffer, it's a local variable on the stack. You don't explicitly allocate this one and deallocate this one, right? You just declare this or define this, then you're done. So when you are in the program, this variable exists. When you are out of this function, this program doesn't exist. So by using local variables using stack, you abstract away allocation and deallocation. So heap is different. Heap is explicitly done by the programmers. You need to use the malloc suite functions to explicitly ask for memory. For example, malloc, canloc, recanloc. So they will give you the size of data you want if there is enough space. And that memory obviously that space is not really on the stack, it's on a heap. So this is useful when you, at runtime, all of a sudden you have to create an object. The object is created because you get some user input, you get some network input. Without that input, you don't have to create that object, right? So for some dynamic reasons. Also in C++, you do not have to use malloc, canloc. You can use C++ keyword new and delete to allocate objects on the stack, on the heap, sorry. So the difference is between new and malloc is the new keyword will actually be used to create the objects. And when you use new, the objects construct function or construction function. Construct function will be called automatically. So there are many different versions of heap implementation. Like I said, this is not a kernel stuff. This is a usernet thing. This is a library thing, which means that to switch to another heap implementation, you don't have to update your kernel. You just need to switch to another library. So it's very easy to do. You don't have to use the default say library. In Linux, you can use that load preload trick to switch to other libraries, actually. So that's why there are many different implementations of heap management or dynamic memory allocator. First one, the DL Malloc. That's one of the famous and old ones. It was integrated in some very old Linux distributions. A lot of textbook, I believe, use this one to teach dynamic memory management. Then PT Malloc is a very, very popular one. I believe on my computer, the libc I have is using PT Malloc. And PT Malloc is based on the DL Malloc, and it supports multi-threading. Then there are many other versions. A Google implemented a version called a TC Malloc. There is a JE Malloc, and also there's a professor, Emery Berger. He's a great computer system guy. Also did a lot of research in security. He is also the author of the famous csracking.org. So he actually implemented another famous memory allocator, Horde. You can find it online, it's open source. My team is actually also working on a dynamic memory allocator for low-end devices. I remember I told you guys, my team mainly work on very low-end devices. Those devices doesn't have an MMU, don't have a virtual address space. So for a long time, those devices, they do not really have a dynamic memory allocator. The reason for that is people feel they don't need that. The stack is enough. But now a lot of those kind of devices are running multi-tenant tasks. You're running tasks from different vendors. So you have to somehow isolate them. And you also need better memory management there. Then security is an issue. So my team, we have been talking about, we implement a secure version of that using a trusted execution environment. And we haven't started that, but we probably will start doing that this summer. Okay, so if you want to find out which implementation you are using, you can do a LDD version, which tells you what libc you are using. For example, this is what I did on my, this is my laptop. This is not the server. I didn't try this on the server yet. So for my laptop, I'm using this libc 2.31. And then I can find the source code of this because everything is open source. Then I can find that the dynamic memory allocator I'm using is actually PT Malloc C2. If you are interested, you can read the source code to figure out how everything works. Okay, so the first question we want to answer is how many bytes on the heap the Malloc chunks really takes up. So for example, when you do a Malloc 32, do you really only allocate 32 bytes? Or there are some other information there? Malloc 4, Malloc 20, what about Malloc 0? Will that work? Okay, most people never tried that, right? Most people never tried a Malloc 0. So obviously, the buffer size returned by the memory allocator has to at least the same size as you ask for. Okay, if it's smaller than what you ask for, there is no reason for them to give to you. However, what most people do not know is, because when you're only using it, you don't think about how this is implemented. Don't know is, besides the size of data you ask for, so memory allocator still needs to maintain some metadata. The metadata keeps the information, how many memory space are there? How do we divide them into smaller chunks? How they are collected together so we can easily find them. Some of them are used, some of them are not used. So those metadata has also need to be allocated and also updated. For example, here I have a simple program. I took this program from the RPI security class. They did a very good job there, so I just took the code. So this is a simple program. We have a main function. We have an array of integers. We call it lengths. And there we have 32, 0, and just 32. Then we have an array of pointers. Well, obviously, they are not initialized because we don't have their value yet. Then we are going to malloc 10 times. And every time we are going to use an integer in the length array. So we are going to malloc 32 bytes, 4 bytes, 20 bytes, 0 bytes. That's it, okay? Then after that, we are going to print out 3 things. The first one is how many bytes we try to allocate there. That's what we try to print. Then we print out the address malloc returned to us for each of those. Then we print out the size between those 2 allocated buffer. Okay, we're going to allocate 10 buffers here. We're going to say if they are adjacent to each other or there are something among them. So let's say, so ideally, what we will have will be something like this. We are going to allocate 10 buffers or 10 chunks. Then the first chunk will at a lower address. The second chunk will be a higher. Then it will go up to the 10th chunk. So because this is heap, we will go from lower address to higher address. This is not stack. So if let's run this code on our server. This is our server. Oops. Size, heap size, 32-bit. Let's run the 32-bit first. When we run this program in the server, you can see we get this output. First, we print out the size of size t. I actually didn't show that here. The size of pointer is also 4. Then say malloc 32 return at this address. And then the next pointer, malloc 4, is at this address. So from malloc 32 to malloc 4, there are actually 48 bytes. But we asked for 32 bytes. The second one, we ask for 4 bytes. It actually, the distance between them is 16 bytes. Interesting is if you do a malloc 0, okay, you do not ask for any memory. It will still return you something, and the 16 bytes to the next pointer. I'm not sure why malloc is designed this way, to be honest. To me, it's like if you give me 0, malloc is just exit, but it is designed this way. If you do a 0, you ask for 0 bytes, it will still give you some space there. And this is the 32-bit, and let's say the 64-bit. So when we run a 64-bit, you can see the size of size t is 8. The size of pointer is also 8 bytes. When we ask for 32 bytes, 48, 4 bytes, 32 bytes. 20 bytes, 32 bytes, 0 byte, also 32 bytes. 64, which is 80 bytes. Okay. So that is what was actually allocated in the memory. A little bit bigger than what you ask for. The reason is the metadata and also for some alignment reasons. So if you check the source code of PT Malloc 2, you can find that the Malloc structure is actually defined like this. There are some internal state T. This is just a size T, actually. So 8 bytes in 64-bit immersion, 4 bytes in 32-bit immersion. It has a previous chunks size. It also has its own chunks size. Then there is a pointer. This is a double link to point to the previous chunk and the next chunk. Also for larger blocks, there is another double link. So what we're looking is actually the header is probably something like this. This part of so it has the previous size, its own size, and the two links. So this is the metadata before the buffer it gives you. So what does this heap chunk really look like in memory is this. This is just another figure of the code here. First is your data, the address Malloc returned to you, your buffer where you can use. And it has at least the size you ask for, right? It could be a little bit bigger for alignment. However, and this here is what the Malloc, the function Malloc, going to return to you is this address. But what under the hood the Malloc function will do is it will allocate the whole heap chunk like this. The heap chunk has the previous chunk size. This is a figure for 32-bit machine. That's why this is 4 bytes. Then it has the the chunk size of itself. So it will be this way. So it's a little bit different from my drawing here. My code here also have a double link. My drawing here doesn't have the double link. But the idea is you need to understand there are metadata before your buffer. And you can say this could be a security issue, because what if you can write this buffer? Then you can overwrite the metadata, right? You can overwrite other heap chunks as well, and also this metadata. And that is what the security risk lies. Let's say another example here. So here we have another example similar to the previous one. We are going to allocate a lot of buffers, and their lengths are getting bigger and bigger. Then for each allocated buffer, we are going to print out that chunk information, assuming they have this format here. So let's see what we're doing. We're getting the address and the length, right? Okay. So we're going to first print out the, let's say, the 2 bytes before, not 2 bytes, 8 bytes. We're going to print out this 4 bytes, then print out this 4 bytes. This 4 bytes, then the data buffers address and the length. I think I changed this code a little bit, but the version I'm looking at right now seems like, oh, this version should work for 64-bit as well, because I'm using size T here. Okay, let's try that. So we go to challenges, we go to chunks, 32. Okay, when we run this, we can see that we allocate those memory buffers, and this is their address. Okay, then we can see the metadata before them. Here we can see the size. The size makes sense. We can also say the previous chunk size. However, they are all 0. I think the reason for that is because maybe the new version of our the new version of PT Malloc is not really using this field anymore. But for a backward compatible, we still leave it there. But we're not really using it. So that's why we get all zeros here. If we go to the 64-bit version, I think 64-bit should work. 64-bit version, you can see previous chunk size is also all zeros, and the size, this one makes sense. This is actually the size of its own chunk. So that is basically how the chunk works. Let's say. So for each heap chunk, there are 2 different states. One state, this is a 32-bit figure. One state is the in-use state, which means this memory is used by someone. And in that state, the chunk structure looks like this. Previous chunk size, its own size, and data. If it's in another state, which this chunk is not used by anyone at this moment, then the chunk will have a different structure. That's why we have this one here. Okay, because this is the definition for the freed one. So for freed one, there is a double link. It has a forward link and a backward link here. It points to its previous chunk and its backward chunk. I believe also in this implementation, it's not really a double link anymore. So let's try this on our server. But you guys understand this, right? Because for different state, you can just define different structure for it. If it's used, then this part will be used as data. If this one is free, not used, then we're basically adding this to a list, and there are 2 pointers in that list. If we use, we try this free 32. Oh, I haven't shown you the source code yet, right? So this is the heap free code. Let's say what we have here. We are going to create 5 chunks here. We're mallocing 5 chunks, you can see. After that, we're going to print, use the function print in use chunk to print the information of that chunk. This is print in use chunk. So this is the structure. This is the format we saw just now, which has a previous chunk size 0 and its own size. That's it. Then we are going to free all 5 chunks here. After we free all 5 chunks, we still have the address, right? We still have those addresses. So we are going to print out their value at those address again. But this time, we're going to print out the previous chunk size, current chunk size, and the first 4 bytes in the data area, which now should not be data anymore, but the 2 pointers. So that's how we are going to do this. We first malloc 5. We first malloc 5 chunks. So 5 chunks will be created on the heap. Then we freeze those things. So those 5 chunks are still there, but they are not in use anymore. Instead, the dynamic memory allocator will update its pointer fields to chain those freed chunks together. That's basically how it works. So if we run this program, you can say, at first, we start mallocing. We malloc 5 memories. And you can see their address and size. And those are their size, those are their address. You may ask why we're showing 31 here, not 32. That's because the least significant byte or several bits. Let me check how many. So here, I'm not sure if this is 1 byte. Maybe this is half byte, just the 4 bits. Those 4 bits are used for, only 3 bits. The 3 bits of the current chunk size is actually used for flags. So they do not mean size, which means size has to be 3 bits. Size has to be 8 bytes aligned there. Okay, going back here. So after we malloc this, we delete, we free all the memories. And you can see that after we free it, previously there was data. We didn't put any data there, so it's basically garbage in the memory. Then after we free, we have this linked table, linked list. Sorry. Let's say the first chunk, its previous chunk is 0. It doesn't have a previous chunk, and its next chunk is at this address. Then this one, the previous chunk is this one. You can say this one is actually this one. This is address. So this one, previous chunk will point to the second one. The previous chunk will point to the first one. The backward, what is the name of that field? Well, this is forward. This is a backward link, I guess. Anyway, so you can see all the backward link, they point to the same address. I'm not sure where that address is. I do not say it here. It's probably just a pointer. It's like a head pointer, I guess. And so this is not strictly a doubled link. It is not really implemented as a double link. It's more like this part is not really used. This part always points to the same address. So it's actually a single linked list in this implementation. Even though it has 2 pointers, only this one is linked. So this one points to here, this one points to here, and this one points here. Right. So this is a single link. And by reading the flags, we can know that those are freed memory spaces. If we do this on the 64-bit version, I wish it works. I changed the code. I think it should work. Let's see. Oh yeah, it works. So we are mallocing 5 spaces, and those are the buffer's address. And the first one after freed, it doesn't point to anyone. That's interesting. The second one where it points to the first one. Oh, it's the same, right? Oh, but even the backward, this one is not pointing to what else is pointing to. But I guess we only care about this one. So this is still a single linked list. The second one points to the first one. The third one points to the second one. The fifth one points to this one. So this is how heap implemented at a high level. Any questions? Today we're not going to exploit heap. We're going to leave that to next week. So far, any questions? Do you understand how this heap is implemented? There are no questions? Okay, if there are no questions, we have a short class today. I will update you on the Slack channel to say when I'm going to deliver the Monday class. Probably this Friday night, I will deliver that one. I will record. You don't have to be there, but I will send you the link so you can join. So homework of this week, we'll have you need to exploit ROP2, 32-bit version, the challenge ROP2, which we talked about a little this Monday. And you are going to play with those heap-free heap sizes programs and explain the output. You check the C code and you see the output, and you need to explain what you are saying here. Okay, I guess that's it for today. See you guys Wednesday next week in person.
Professor?
Yes, go ahead.
Could I ask you a question before class ends?
Sure.
I was it's unrelated to class. I was just I'm
Okay.
filling out.
Then do you want to go to another private room or?
Actually, yeah.
Okay, then let me just stop the recording first.